Okay, now let's start with the new topic of the day, and that is a recap in probability theory. So I will give you a complete overview, at least of the elements of probability theory we will need later on this class. Obviously there is more out in probability theory. You can give a whole lecture or 2 lectures about probability theory. I will just concentrate on the most important elements we need, and that has to do with some distributions, in particular the Gaussian distribution. We will talk about how to compute expectations of a distribution, the variance of a distribution. We will talk about correlation and covariance. We will talk about what is a random variable and some other general elements. So that is what I want to do over the next 90 minutes basically today. So let me start with very basic elements. It's like some definitions which you also find at the first or the first pages of this chapter. It's, I think, chapter 3 in my notes. So usually for a random variable, and I will define in a second what random means. So a random variable, we use capital letters. So for instance, X or Y or Z. And to define what random means, well, we first start with a certain basic set. Yeah, let's call it a basic set. And this basic set is called omega. Greek letter. And this omega contains all possibilities of my variable. So suppose the random variable is a stock. Yeah? It's a stock price of Microsoft or Apple or SAP. Well, then you would say all possibilities of the stock price are all prices from 0 up to infinity. That would be in my omega set. Actually, in my omega set is even more. Let me explain this. I choose the following example. If you roll a dice, yeah? So if you roll a dice, you would say, well, in this omega set, if I roll it, it pops up the 1, or the 2, or the 3, the 4, the 5, or the number 6. These are the obvious outcomes if I roll a dice. But actually, these are not all. Suppose I roll the dice, and then this is absorbed because it rolls over here, like in a black hole. It's gone. I can't see it. Yeah? So let's say this is the empty set. Yeah? It's gone. Or I roll the dice, and then it remains, it falls here on this side, and you can see, if you look from the top, 1 and 2. Yeah, you can see both. You can see 1 and 2 because it's on the kink. Yeah, the dice is on the kink. But maybe in the other case, it's also on the kink, but you can see 3 and 4, and so on. Yeah, you see there are many possibilities which are not realistic actually, but omega contains everything. Yeah? So that's in my set omega. All possibilities. Due to the fact that we are usually just interested in the realistic outcomes, we have another set. We call this usually F. Yeah? And that is what we call F is a filtration. So this set F, yeah, contains, you can say, the realistic events, yeah, the most likely outcomes. And we we are not looking to these really rare and absurd or very unlikely situations. Yeah? So it's a set containing realistic outcomes. Actually, this filtration should have 3 properties. So there are certain properties of set F, my filtration, and we only call it a filtration if these 3 properties are fulfilled, if we are in line with these 3 properties. The first property is the empty set is also in my filtration, which seems for you, well, that's not likely, right, that I roll a dice and it falls into a black hole, but this has it's necessary to make the whole mathematical model consistent. It's like the 0, yeah, in the real numbers. What is 0? You can say that's nothing, but it's quite hard, because if you look back into the history of mathematics, at the beginning there was no 0. And the whole system of mathematics first evolved if someone got the idea, why not introduce 0 as an element? Yeah? When the first guys started, before Pythagoras and the Greek guys, they just thought, well, mathematically we just have objects like 1 pen or 2. They never thought 0. But then they implemented 0, and then the mathematical building and model really evolved. That is very critical for the whole framework. And that's similar to this empty set here. Yeah? The second condition is if there is an event omega I. So what is omega I? Maybe I have to say, so this is a small omega, that's a capital omega, this is small omega. Well, this is one event. For instance, you roll the dice and you see the 1. Yeah? You roll the dice and it's 1. Then you would say the small omega is what actually occurs. That is indicated by the small omega, yeah? 1 in this case, or example. So if the omega I is element of my filtration, yeah, if the 1 is in my filtration, then the complements, though the opposite numbers, realistic numbers, are also in my filtration. In other words, if 1 is an element in my filtration, then the other realistic events, 2, 3, 4, 5, and 6, the empty is anyway in, are also elements of my filtration. That means C, the complement, that's the opposite of what we got. Yeah? If we take the example of a dice, 1, opposite are all the other possible outcomes, 2, 3, 4, 5, and 6.
Is complement with E or I?
Complement?
Yeah, after L is an E or I?
Mit E, complement. Yeah, it's complementary. Yeah. So it complements the list, right? If I have 1, then the filtration contains the other. That's the second property. And now the third property of my filtration.
Okay.
Yeah.
So if you say all the complements, then even it is if it's on the king, right? Or do you exclude that specifically?
Well, if the filtration is defined containing only the realistic outcomes or events.
No, we're not with F, but we're with omega, small omega, right? So that's like, in the end, it's part of the filtration, but small omega itself could contain like even the unrealistic ones, right? If it's a complement.
It could, but if I say it's an element of F, it just my filtration probably consists of this.
Okay.
Yeah, and if 1 is inside, then the others are inside. You will see over time it gets a little bit more complicated because the filtration is not a static set. They also change over time, but let's wait for this. Okay. Third property, well, if we have some events, let's call them omega I, and they are in my filtration F, then the union, that means all these single events all together, yeah, from I to infinity, or to all the, if the set has just n elements, you can say I to n of my omega i's are in my filtration. So this symbol is a union set. Yeah? So for instance, if I have set A and if I have set B, you know, this is the intersection that is called A intersects B. Yeah, that would be this set. And the union, I can say A union B is the overall, yeah, taking both together. So if I have an omega I, the one, if this is in my filtration, then also the union of all other possible events, 2, 3, and 4, they are all in my F. That is what this third condition, satisfies or tells you.
You said that filtration is likely or something close to reality, so how can it be infinity?
Sorry?
I'm just trying to remember, we're using the infinity there when we're talking about filtration, which is actually something that is rather realistic than anything possible. So can it be reality?
I told you while writing, if this filtration is finite, you can say it's just n elements and it's first element to the nth element. But it's possible infinity. That's possible. Even it's just realistic events. You know, the stock price can be 0, it can be 1 million, it can be 1 billion, it can be 1 trillion. I don't know, maybe it can be infinity in extreme. Yeah? So it's just the mathematical convention. Yeah? So for you in the simple framework, this is clear, but the others also, the infinity symbol is also possible here. Okay, so if these three properties, if my filtration has, or if this set F has these three properties, then we call it really a filtration. Yeah, that's usually the properties that makes a filtration. And now we have just some terminology which is important, not really. Basically, you don't understand all the insights, but if you read a book, they always pop up, and therefore it's good to know what they at least roughly mean. The smallest filtration, the smallest filtration F is called a sigma algebra. Suppose there is a filtration which is the smallest possible, so it contains the empty set and it contains some outcomes. The smallest possible filtration is what we call a sigma algebra, and we use the symbol sigma, yeah, sometimes with some symbol for this filtration F or some other set. So the smallest filtration is called a sigma algebra, so that is one. If you have maybe read it already, sigma algebra, so don't worry, it's just a very particular set of objects. And then there's another set which sometimes pops up in books, which is quite complex actually. Even most of the mathematicians don't understand what it is, but I try to give you a kind of understanding. Suppose this omega are just elements on the real line R. Yeah? So the omega just contains numbers on the real line. Not blue, not white. You know, omega could contain everything. Yeah? Even if I roll the dice, maybe it pops up, the dice is blue. You can see nothing, just blue. Possible. So, but now suppose omega is the real line. Yeah? In this case, we call, if this is the case, then the filtration is called a Borel set. Yeah? And we use the B for this. Yeah? Then we are not using the letter F, and we are not calling filtration, we call it then a Borel set, yeah, that has these properties. We use letter B. And the smallest Borel set, you can say, is a Borel sigma algebra. Borel sigma algebra, analog to my definition here on top. Yeah, sigma Borel. Well, in my lecture notes, I have a kind of couple of bullet points that tries to give you some idea of these Borel sets, but once again, this is a very complicated object. So even filtration, you see, that's not easy to understand, and even omega, you know, that contains everything is, you know, quite hard. But what is important, just to distinguish a little bit these elements, to keep in mind that omega is everything, F is the interesting events, and that brings me to a very important implication. If we look to omega and F, yeah, we call this a space. This is a so-called measurable space. Yeah, that's a space containing all the possibilities and looking only to the interesting possibilities or events in this universe. Yeah, that's what we call a measurable space, because F, this filtration, is measurable. That's terminology or definition. So that's what we call a measurable space. And in a second, I will define a probability space, which you all have heard about. Yeah, and a probability space consists of omega, F, and a probability measure P. Probably in statistics, you just talked about this omega and never about the F. That's a problem. Yeah, but now we are very precise here. So a universe set of omega and F is called a measurable space. Now let's talk about what is a probability measure. A probability measure, usually we use the letter P. Well, a probability measure P, in the end, yeah, that gives you a probability, a likelihood. What this does, it is a function. And it is a function that is relating all the events of my omega set, yeah, in the general case, yeah, all possibilities, and plot all these possibilities on a set between 0 and 1. It gives all the possibilities a probability, a likelihood. And this P, yeah, is a function that is describing this relationship, event, and gives them a number in this range of 0 and 1. So you can say there is some omega, yeah, some omega, little omega, yeah, some small omega. You can say P of omega, that the 1 pops up if I roll the dice, yeah, and then the probability measure plots this likelihood that the 1 pops up, gives this case a probability, yeah, between, in this range of 0 and 1. Maybe if it's a fair dice, the likelihood that 1, 2, 3, and 4, and 5, 6 pops up is a 6.
So what you just said before, even the omega contains the likelihood that somehow, for example, the dice changes its color.
Yeah.
So in the end, you could do it infinite many times. It would never change its color from white to blue, right? So it would not be between 0 and 1, but it would be 0, right?
Yeah. And therefore, usually to define a probability measure, if you read my lecture notes carefully, or if you already prepared my lecture notes, this definition starts, suppose we start with a measurable space, yeah? With a space omega and a set F, our filtration that contains a realistic event. And now we plot these, and obviously what we then plot are based on our filtrations, the likely events, yeah? And if we have this, then we get a new space which contains omega, my filtration, and P. And that is what we call this is a probability space. It's a probability space, yeah? And P is called a probability measure. P is called a probability measure. Yeah, so omega f and P is what we call a probability space, and P is the probability measure. And in the end, it's a function. Yeah, it's like f from x, f from the event small omega. Now we come closer and closer to the more important points. You know, that's just making the terms clear. The most important parts which we later on need is to understand a random variable, yeah? Which I already mentioned here in the beginning. Yeah, I said, well, a random variable, we use always capital letters like X, Y, or Z. Yeah? And in the end, you can say X of omega. So the X is the outcome of a certain event omega. It's like the probability. Yeah? You don't know when you roll the dice whether it's 1, 2, or 3. That is random, right? You can see the 3 or you can see the 5. But the outcome is dependent on the likelihood is dependent on what it pops up. So if we have an unfair dice, yeah, let's say always you can, or if you roll it and more, the likelihood that the 6 pops up is higher than the other numbers, yeah, well, then you have a higher likelihood for the 6 if omega is equal the outcome 6. Yeah, and this random variable gives you the likelihood of this particular event. But it's uncertain, obviously. And now you know from your statistics discussion there are so-called distributions, yeah? Probability distributions. And that is my next point. We have to discuss the probability distribution. So let me talk about the so-called probability distribution. And we have to distinguish probability distribution to another term. Have you heard also probability density or the density function? Never. Then you will hear it now. Probability density. Okay. So let me start with a probability distribution or density you all know. Let me do this graphically. The probability distribution for the so-called normal distribution or Gaussian distribution. Yeah? So standard normal distribution, the so-called standard normal distribution. Yeah, some people say Gaussian distribution. And probably when you have seen so far the Gaussian distribution, people plotted the following curve. Right? This is what we say. Well, there's the likelihood that the outcome is very small is low. The likelihood that the outcome is that the high numbers is very low, and most likely it's around 0. Yeah, that's the highest likelihood. But this is not the distribution. This is a density. This is a probability density function. And for this density function, we use a small f based on my random variable or my probability measure. Yeah? You can say, let's call it small fx from x. The distribution, which is here on the left-hand side, we use the capital F. Yeah? And that looks, for this normal, standard normal distribution, it looks like this. Here's a half, and then it goes to the line 1. It starts here in 0, up, and it looks like this. This is the distribution function of a standard normal distribution. So now let me explain the relationship. This is capital F, this is small f. And that means the density is a derivative of the distribution. Take a look. Here the slope for small numbers is almost 0. The slope for very big numbers, as you can see, it goes to 1, is 0. Yeah? The density is the derivative, and therefore the slope, yeah, if the slope is small, the density is small here and small here. And you see the greatest slope is here in the middle, at a half. And that is the greatest number. The highest probability is here. So, what does this picture is telling us? Well, if we take into account all possibilities, all x possibilities, well then, the probability is 1. So in other words, if we measure the probability of all possibilities, let's say omega, yeah, so we are here, very far here, it sums up, it converges to the number 1, yeah? So this gets close to 1. For a very rare event here, well, it's 0. This is a very important point. So how can we find the probability if we have the density? I'd already mentioned that if we calculate the derivative of this in respect of x, we are here. And if we have this, what we have to do is the integration. And therefore, the definition of the distribution is always the integration from minus infinity to a certain point, let's call it x, of my density function. Maybe give them the threshold another name, let's call it until t. Then we can keep the x here as our integration constant. So if we integrate from minus infinity until a certain event, that gives me the probability distribution function. In other words, yeah, the integral of this is this, the derivative of the distribution gives me the density. I will do an explicit example in a second, and then I think it's a little bit more clear. In general, is there anything to add? Yeah, I have to tell you, because this is obviously the most important part about this is the properties of the density function. This is what you have to keep in mind, otherwise you are lost later on. Properties. Properties of f from x. So properties of the density function. The first property, as you can see, it's always greater equals 0. Yeah? Every event has a positive probability. Maybe it's very small. The likelihood is very small, or it's very high. But it's always positive. The density function is above 0, as you can see, and gives every possibility a positive value. So every point you can see here, it's positive. That's the first property you have to keep in mind. The second property, if we calculate the integral from minus infinity, so if we start way on the left, and if we integrate up way to the right to plus infinity, dx, yeah, so if we integrate what is here below this function, if we do this integration from minus infinity to plus infinity, what is the value? Well, it's 1 in the end. So the area below my density function, and that is true for all density functions, is 1. And that is what you already know. Probabilities always add up to 1. Yeah? Every probability is between 0 and 1. It's positive, it's between 0 and 1. And the sum of all probabilities adds up to 1. You just discussed it in a discrete sense, right? You say there's a probability half this likelihood. If you flip a coin, likelihood for the head is a half and the other side is a half. That is a discrete. Here we have a continuous variable, same properties. It's always, every event is positive. It's between 0 and 1. And if we add up all the outcomes, the probabilities add up to 1. And that's the area below this density function. That's the third property, the second property. And then there is a third property. Right. The third property is that this function, the density, is continuous. So f from x is a continuous function, which is obvious from this example for a standard normal distribution, but that is what we always assume here. These three properties, please keep these three properties of a density function in mind, because I will use, in the next calculations I do with some examples to make this clear, I will use these properties. They are very elementary. Density is always greater than 0. The integral below the density function from minus infinity with plus infinity adds up to 1. That means all probabilities add up. If we sum up, if we sum up all the probabilities, they will sum up to 1. And it's a continuous function. So this is, I would say, this is the assumption or the key property we will use several times today, and when we do the Black-Scholes derivation.
I just have a question. Maybe it's just me because I did an education in Germany. So there's an integral part, and underneath there's minus infinity.
Yeah.
And why do we have t instead of plus infinity?
Well, I just assume we start from way below on the left, and then we integrate to a certain event t. Yeah. So if we are interested, what is the likelihood? What is the probability that this event t, well, t can be here or can be here, that a certain event appears? That is what we are usually interested in. We want to know the probability based on my distribution, how likely this event t is, and then we integrate just until t. Yeah. This is just a certain element or event. Yeah. How likely it is that the 4 pops up when we roll a dice. Yeah. Then the t would be we integrate up to 4, and we are interested what's the probability of this, given there is a distribution of the outcomes of rolling a dice. Okay, so keep in mind, we distinguish probability distribution. We use capital F for this, and a density function, we use the small f for this. There's a relationship between both. The density is the derivative of the distribution function. And the density has these 3 properties. So now let me show you an example, or do an example. What I'm going to do next is I will discuss the issues we have talked about with an example. So I will give you a distribution, a density function, and then we will compute the distribution, the probability distribution based on my density. And the density function I will give you is a probability density for an exponential distribution. Usually income is distributed according to this distribution, and the density function looks like lambda e to the power of minus lambda x. And due to the fact that the x, if this is a distribution of income, you probably, to make sense of this, we have to assume that x, income, is positive. Otherwise, this distribution, if income is negative, would be 0. Yeah, it only makes sense to talk about income, positive income, and look to the distribution of this. So this is the density function, yeah, the small f, the probability density. And now I want to compute, or I compute. That is what I'm going to do. So this is example. The distribution function. So before I can really start here, I will introduce one concept which I have not talked about so far, but which is also frequently used in theory, in probability theory. And this is the idea of what we call an indicator function. Indicator function. And we use letters either 1, indicate, or we use just the E. Yeah. And so what is an indicator function? What does this mean? Well, it's not too difficult to understand. Well, the indicator is a function which is either 1 or 0, and it is 1 if my event omega or my income x is in my set, let's say omega. If the event is not, well, omega does not make sense here. In my set, let's call it A. And if omega is not in my set A, then this indicator is 0. So in other words, if I have certain events, yeah, as long as we have, let's say, all the events here on the left-hand side are in my set, then this function is 1. And then let's say up a certain threshold, the omegas are not in this A, so this is A is containing all the numbers from -infinity up to this, then this function would be 0. And the reason why I introduce this function, well, this allows me to write down this density function, because this function, as I already mentioned, makes only sense for positive income. So as long as x is positive, then this function is 1. As long as x is 0, this function gets 0, and then I just write the density function as follows. I say, well, that's my density times my indicator of x, yeah, and maybe you can specify the interval from 0 to infinity, yeah. So if x is 0 to infinity, positive, yeah, then this is 1. You have this function, yeah, because you multiply just with 1. If the x is not in this interval, then this indicator function gets 0, and then 0 times something, then the density is 0. Now this is another way to write it in a compact fashion. So now back to my ultimate goal. The ultimate goal is to find the distribution function. So what we have to do, we have to integrate from -infinity up to a certain level. Let's call this level t, yeah, certain income. And then we write down here our density function, which is lambda times e minus lambda x times my indicator dx. So to get the distribution function, we have to compute this integral. So let's do this. First of all, you see this integral makes only sense if x is positive. So if I write the indicator now outside or in front of the integral, then it makes only sense if I integrate from 0 and not from minus infinity. Because if I start at minus infinity, you know this integral is 0 anyway because of my indicator. So this integration makes only sense for x 0 to t, right? And then I bring this indicator out because I considered the boundaries here. And inside we just have this. So now we have to integrate this. Well, lambda, you know, this is just a parameter and we integrate over x. Yeah? So you can also bring the lambda logically outside. Yeah? So we just have to integrate the exponential function. Well, the integration of the exponential function, that keeps, right? The derivative of exponential function is the exponential function. So we can, of course, write it down immediately. And then, if we go back, so if we go back from here to here, right, we have to do the derivative. So we have the exponential function, and then the derivative of my exponent is minus lambda. Well, here we have lambda, but we have not minus. So obviously then the integral must be minus the exponential. If I do now the derivative, I have this, and the derivative of the exponent is minus lambda. Yeah, the minus then goes away, and we just stay at lambda times the exponential. So this is the integral of this, and now we have to evaluate this at our boundaries, 0 and t. So first I plug in the t, then we have minus e minus lambda t, and then minus e minus lambda at the boundary, lower boundary for x 0. So, what is this? Well, if I have the exponential function, in the exponent I have 0, so e to the power of 0 is 1. Yeah? This is 1. And this minus and minus is obviously plus, so I can write it down as minus this. Yeah, because minus minus is plus, therefore I switch the order to have the plus 1 here and then the first term here minus lambda until, if I compute it until my t for a specific t, but in general, you know, in general we can take this t, can be any amount, so you can go back and switch back to my x. So if I generalize this, yeah, this is now the density for a certain event or outcome or income. But in general, the distribution function for x, for all possible, you can say this t, yeah, is anything is x. So this is now the distribution function corresponding to the density function I wrote down. Can we go back? If this is the distribution, then the derivative of this, if we calculate the first derivative, we should get what here is on the top left-hand side of my board, right? So if this is my capital F, yeah, you see, this is capital F. So let's compute the derivative of my capital F in respect of x, which is then my small, which gives me my small f. Well, the derivative of 1 is 0. Minus derivative of the exponential is the exponential. Then the derivative of what is in the exponent in respect of x is minus lambda. That minus and minus gives me plus, so just lambda in front, and then we have also the indicator. Well, and you see immediately that this is actually the function we started. This is my density function. That's a density for an exponential distribution. And that is the distribution function, the exponential distribution function. So can you see the relationship between capital F and small f, and how to get, if you have capital F, how to get the density, and if you have the density, how to obtain or calculate the distribution. Yeah.
Just one question. The second step, so where we eliminated lambda, why can we eliminate lambda? Isn't it minus lambda squared e to the power minus?
You mean from here to here?
Yes.
No. So from here to here, I just do the integration.
How we do the integration? Yeah.
There's no elimination.
Okay.
So in other words, if you are here, the derivative, which is the other side, should get this. So if you take this function, if you calculate the derivative, you know that's minus the exponential times the derivative of this, which is minus lambda. Minus minus is plus, and therefore you end with lambda is equal. So derivative is the opposite of integration, and it should work in both directions if we are correct. That's the way to check whether your integration was correct. Probably what you have in mind, and we will have an example in class in a minute or in 5 minutes, when we have also an x here, then we have to do the product integration, which is a little bit more difficult, so wait a little bit. But this brings me to my next point. My next point is now to explain what we call the expectation and the variance of a variable, or of a random variable. Expectation. Expectation. The expectation, in other words, is, in simple words, it's the mean value or the average in discrete terms. But here we have continuous, right? All the functions we use are continuous functions. And that is probably the new. What you did in statistics was always discrete. And you called an expectation, what we call expectation, the mean or the average. The reason why we do it in continuous is because the whole finite theory is based on continuous mathematics. And therefore we need these continuous analogs to discrete stuff. So let me explain. For the expectation, we use the symbol E, with 2 lines here, and we call the expectation of my random variable x. How can we calculate this? Well, we consider all possibilities from minus infinity plus infinity of my random variable given a certain density of this random variable, a certain distribution, which is reflected in the probability density function. This is the definition, I will give you an example in a second, of how to compute the expectation value of a variable. And we follow with this example, but let me first also mention what we call the variance. The variance, here we use the letters var of my random variable x, or sometimes sigma square. And you know, sigma, so the square root out of sigma square is called the standard deviation. Yeah, this sigma is called the standard deviation, and with the square it's the variance. Just to mention, this sigma has nothing to do with the sigma algebra. Yeah? This sigma gives you the variance, the distribution, the range of my random variable. Yeah? And how can we compute this variance? Well, in the end, the variance is based on the expectations, and it turns out that it is the expectation of my random variable subtracted from the expectation of this variable squared. Squared. This can be simplified. So there is a proposition which you find in my lecture notes by Steiner, a guy who showed, quite easy, that this is the same as the expectation of x squared minus the expectation of my variable squared. That is also the variance. Well, you see, if we know the expectation, we just have to square this number. That is the second part. And what is the first part? Well, we use the idea of how to compute an expectation, which is the integral from minus infinity plus infinity, but now it's not just for x, it's for x squared times my density. With this, I will obtain a number for this, and then I can subtract the average number, which I obtained from this, squared. And then I have the variance, which is a number that gives me the range of outcomes of my random variable. The expectation is something like you call the mean, the average, and the variance, probably that's the same terminology you used at that point, gives you some range. So let me now, once again, go back to this example and calculate the expectation for my exponential distribution. This example. So I will continue this example and I will calculate the expectation. Question?
For the expectation value of x squared, why do we only, yes, the very last one, yes, exactly. Why do we only take in the integration only x squared times f of x and not x squared times f of x squared?
Yeah, you see, the definition of the expectation of my random variable x is x times density. If I calculate the expectation of x squared, then it's x squared times density. The density remains, it's just the x variable which is different. Yeah, you see, x squared, and therefore x squared is here. The density is always necessary for finding the expectation, but it's not affected by this. You know, this is just what you have to take for granted. Yeah, that's it. This is how the formula look like. We will do an example, and that's the definition. Yeah, and it makes sense, or so it's given. You can say, don't worry. That's how to compute the mean value. Yeah, how to do that in discrete mathematics? You add up all numbers divided by all cases. And here's the integration of all probabilities over the density. That's an expectation. So let me show this for my example. So let's continue the example for the so-called exponential function, density function, which, as you already know, is lambda e minus lambda x times this indicator, so only for positive income. And I want to know what is the expectation of this density function. So how can I find this? Well, I say the expectation of a random variable that is distributed according to this density is, according to my definition, the integral from minus infinity to plus infinity, my random variable x times this density function. So let's write it, just copy, paste, lambda times e minus lambda x times indicator for my variable x from 0 to infinity dx. Right? I just substituted now the density function inside my integral. And next, I do the integration. Similar to this case. And first, once again, when we have an indicator function, we always take first a look to the indicator and we see, well, this integral makes only sense from 0 to infinity. So even if the expectation demands me in general to integrate from minus infinity to plus infinity, from minus infinity to 0, this integral is 0. So I can skip this. So I bring the indicator outside, and at the same time, I just integrate from 0 to infinity, and then we have x lambda times e minus lambda x dx. And now for the first time, we have to integrate this. This integration is a little bit more difficult. Why? Because now we have a product. We have an x here, and we have an x in the exponential function, in the e function. That is what we call product integration, or partial integration. There are different words. And now we have to remember the rule. And as you know from my macro class, I know nothing by heart. But I can derive this rule easily. Why? I show you. Maybe I take some space here. Yeah? So how can I find the integral rule? Well, you can look to a formula book, yeah? I can also look, but I can develop this without looking. How? Well, I have to do the integration of two terms. So suppose we have a term which I call u and v. And now what I do, I calculate the derivative of this. So I calculate the derivative of a product. And the rule, this is what I know. This is u prime times v plus u times v prime. But this is probably what you all know. The rules of derivatives are far easier. Right? That's differentiation of a product. So now we do the opposite. We do integration. So in the end, what I have to do here, given this rule, I have to integrate here, here, and here. Then the integral of a derivative, well, that cancels out. We just have to look what is u times v at the two boundaries. So this, in other words, u times v at the two boundaries, let's call them a and b, yeah, if we integrate from a to b. And then we have here, here we have the integral u prime v plus the integral u v prime. And now I just bring this first integral on the other side. Then we have u times v at my two boundaries minus the integral of u prime times v, so this on the other side, is equal to the integral of u v prime. And that is the rule you will find in the formula book for a product integration. So what we have here, we have a u and we have a v prime. Yeah? And we have the integral, this. And now in the next line, I use this formula to write it down what is here on the left-hand side, which is the same. To write it down, what is on the left-hand side, so the u is, as you can see, lambda x. U prime is the derivative in respect of x, which is just lambda. If this is v prime, if v prime is this function here, e to the power of minus lambda x, then what is v? Well, v is the integral of this function. Well, let's think about the exponential always is the same. And the integral, well, does this make sense? Of this function v prime, that this is the integral. The exponential stays, and then we have the derivative, which is minus lambda. This minus and this minus gives me the plus, and then I have on top a minus divided with this minus gives me this. So this is the integral of this. Or you can go back. Yeah? If you calculate the derivative of this, you obtain this. So if we know u prime, v and v prime, then we can use this formula for product integration. So let's, in front you see there's my indicator function. That is simple. And then we make a huge bracket. And the first term now is u times v. Well, what is u? Lambda x times v. That is this. Times minus e lambda x divided by lambda. And we evaluate this on our two boundaries. What are the boundaries? Well, 0, infinity. Minus, according to the rule, the integral from 0 to infinity, u prime times v. Well, what is u prime? That's just lambda times v. V is this. So it's minus e minus lambda x divided by lambda dx. That is possible to simplify. Lambda in the denominator, lambda in the numerator, minus and minus gives me a plus. Close the big bracket. Next line. Still, we have the indicator in front. And then we have this big bracket. Well, now we evaluate this term at the two boundaries. You know what we have to do? We have to substitute the upper boundary for x minus the lower boundary. The problem is, if we substitute the upper boundary, which is infinity, usually we don't write infinity now for x. We say, well, this is the limit for x to infinity of this term. Divided by lambda, minus, if we substitute in 0 here, well, you see, 0 times anything here, it's 0. Yeah? So this is now this term, then plus. Now we have to integrate from 0 to infinity. So what is here? Here's just the exponential minus lambda x. So we have just this, and we have to integrate. Well, the integral is what we already did here. So the integral of this is actually this v function again. It's e minus lambda x divided by lambda, and at the boundaries 0 to infinity. I do my best. But this is basic, you know. That is what I did in high school. Up and down, up and down, up and down. That's not university mathematics, really. That's elementary. You have to wait. Next week we move into university mathematics when we talk about stochastics. Is there a question so far? So it's classical integration, yeah? I do just classical integration so far. Okay, so let me continue this line here. So once again, it's equal to my indicator. Well, we can simplify the first term here because we have lambda in, maybe I use another color, we have lambda in the denominator here, and we have it here, up here. Then it's a little bit simpler, and it just looks like x to infinity. It is x times, well, let me write the minus here in front. So it's minus x times exponential lambda x. Zero, well, we skip, that's 0, plus, now we have to substitute again the two boundaries in this function. If we substitute in infinity, we use once again the limit function. We say x goes to infinity for this term, which is minus e minus lambda x divided by lambda for x infinity, minus gives me plus e minus lambda x, 0, yeah, lower boundary is 0, divided by lambda, this. So I just first boundary minus gives me the plus, second boundary for x 0. So take a look to the last term. E to the power of minus lambda 0. So in the exponent there is 0. E to the power of 0 is 1. So what we have here, you can say, is 1 over lambda, right? Because this is 1 over lambda. So the last term, let me write down, if you all agree, is 1 over lambda. So now let's take a look to this term, to this. So what is this term if x goes to infinity? Well, you see there's a minus here in the exponent. So if we write the exponential function in the denominator, then the minus gets a plus, right? We can write down this as minus 1 over lambda times e lambda x. Yeah, if we bring this down, then the minus is not here, it's a plus. It's just now in the denominator. And if we now think about what is the limit if x goes to infinity? Well, the exponential, if x is very large number, a very large number in the denominator, what is then this, the fraction? 0. This goes to 0. Yeah? In other words, we can neglect this factor because in the limit, this is very small. It's 0. Can everyone follow me here? Okay, so I just, to make it correspondent, I say we have find that this is 0. And now we have to think about the first term here. Well, for the first term, I will copy it because this is a little bit tricky to see. So it is minus x e minus lambda x, right? So the first term is just copy paste. And the final discussion we have to do now is this. But there is a question? No question. Okay.
I just wanted to tell that probably it's also 0 because exponential function grows faster than
Yeah, that's right, and that is.
number divided by bigger number.
Yeah, but it's yeah, your argument is right, but I will show this. So what do we have here is we have the limit of x to infinity minus, well, we have x, and here we have once again the minus in the exponent, so let me bring it down in the denominator, then the minus is plus. So we can write this also like x divided by e to the power of lambda x. So and now I ask, what is happening with this term if x goes to infinity? So if you look to this term or this fraction for the first time, you say, well, this is infinity, this is also infinity. Well, is that infinity divided by infinity 1 or so? No, that's not that does not really help, but there is a rule to find the limit, and that is a rule by L'Hospital. And to see what the limit of such a fraction is, we calculate the derivative of what is in the numerator, and we calculate the derivative of what is in the denominator. So let's do this. So the limit for x to infinity minus. So what I'm doing now, I calculate the derivative of what is here. What is the derivative of x? It's 1 then. What is the derivative of this in respect of x? It's lambda e times lambda x. The exponential remains, and we just have to do the derivative of what is in the exponent in respect of x, which is lambda. And now I think everybody can see if x goes to infinity, this gets very large. That is infinity, and 1 over infinity converges to 0. And therefore, this term is also 0. And now you can see if this is 0, if this is 0, and we just consider the positive x, we can also, you see that it's just 1 over lambda, so it's independent of x, so the expected value, the expectation value is 1 over lambda. Yeah? We calculated the expectation here, full calculation. We calculated the expectation value of my random variable, and this random variable is distributed according to an exponential density function. And we find that the expected value is 1 over lambda. So if lambda is 3, yeah, then the expected value is 1 over 3. So far I have no numbers here, but go. So this is now my expectation value. Yeah, and basically what we did, we used the assumption of the expectations, the integral from minus infinity to infinity, we substituted in the density, and then we did the integration, and after some logical reasoning, 1 over lambda popped up. And we are happy. And you can read again this example and more examples. I did the same calculation, expectation value for other distributions in my lecture notes. You know, we have Pareto distribution, Cauchy distribution, we have log normal distribution, there are binomial distribution. Yeah, there are so many distributions, and for every distribution you can do the same calculation to find the expectation value. Why is the expectation so important? Well, it gives us an idea what is the most likely outcome of my random variable. The average. That is the expectation. Yeah? Okay. But wait a second. I think everyone is convinced that this computation is quite sophisticated, right? And therefore, I give you a new approach. And with this new approach, we can simplify the calculation of expectation values and variance. Because, you know, if you want to do the variance, you have to do the same integration for square terms. Yeah? But I will show you soon, yeah, another approach. And this is called the characteristic function, or the Fourier transformation. If we transform my density function into a very nice form, then we get a new function, and with this function we can easily compute the expectation, the variance, and even the higher moments. But it requires to do a transformation of my density function, the so-called Fourier transformation.
You mentioned the other or the other distributions. Is there a link between these expectation variables, or are they completely different?
They are different.
No, of course they're different, but is there like...
I will give you some examples at the end, because we will discuss explicitly at the end of today's lecture the normal distribution once again. Yeah? I will compute the same for the normal distribution, and then you see that there are differences. Yeah? So I would say wait a minute and you will see difference of expectation values for different distribution or density functions. Mm-hmm. So before I do this, what I already mentioned, this nice transformation, I will introduce two other terms what we need, and that is the so-called covariance and correlation. So far, I always assume we have just one random variable, one stock. But usually in reality, obviously, we have not only just one stock in my portfolio. You have in your portfolio Microsoft and Apple. And as long as you have two, well, you have to think about, also mathematically, also in the real world, well, how are these two correlated, connected? Yeah? And for this, we need the so-called covariance and correlation. The covariance is indicated with this for two variables. Let's call it x and y. Yeah? Two random variables. Could be stock A, stock B, or stock X and stock Y. And what is the covariance? Well, the covariance is defined as the expected value of x minus the expectation of x times y minus the expectations of y. This is the variance of x, variance of y. Somehow, you can simplify this again as the expectation of x times y minus the expectation of x. Well, that is what we calculated here for this case, and the expectation of my other variable y. So this is the same. It's just you can prove this just by multiplying it out. Yeah, these two brackets, and then you will see that this is the same. So to find this expectation of x or y, well, that is what we already talked. But what is this? Well, I will just give you an idea. We will not compute. That is a little bit too. But you know, if we have to do the expectation of x times y, we just use the same definition. Well, in principle, it's the integral from minus infinity to plus infinity of x times y. But now, well, we cannot use just the density of x or the density of y. We have to use what we call the joint density. So there is a joint density function covering both. And therefore, in the end, yeah, we have to do a double integration for dx and dy. That looks good. And if we have 3 random variables, we have 3 integrals. If we have 4, we have 4 integrals. You know why sometimes the math books look so sophisticated, but it's very simple. It's just because we have 2 letters, we need 2 integrations. Yeah? But anyway, we will not do this explicitly. By the way, if you're interested, I have also an example of this in my lecture notes. So this is the expectation of 2 variables. The covariance is always a number between plus infinity and minus infinity. If it's very large, that means there's a positive covariance or correlation, or a negative. And due to the fact that this range, plus infinity, minus infinity, is not very meaningful, what we usually discuss or use is a so-called correlation coefficient. So correlation coefficient. And here we use rho. And rho is defined as the covariance, and it's normalized by the variance of the 2 variables. And then this correlation coefficient is always a number between +1 and -1. That is what we call the correlation coefficient. So if we have 2 assets, let's call it x and y, and suppose they are close to 1, yeah? So they have a positive correlation, and then we have certain outcomes for my random variable, and you see, well, all the combinations of x and y are on an upward sloping line. Then we would call there is a correlation is close to 1. That means they are closely connected. If x goes up, y goes up. Or if x goes down, y goes down. Positive correlation. If they are negatively correlated, yeah, we have x and y again. But now my correlation is going to -1. Well, then the negative correlation, we have once again a scatter plot, probably looking like this. If x has a high return, then, if y has a high return, then x has a low return. Or the other way around. If y has a low return, x has a high return. That it means a negative correlation. They are negatively. If one is outperforming the market, the other one is losing. Yeah? That means negative correlation. In the case of rho is almost 0, well, that means there is no correlation. Yeah? If we have a scatter plot that looks like this, just a cloud of dots, you say, well, there is no correlation either up or down. That is what we call uncorrelated. These 2 assets, x and y, the returns, if you say this is the return rate of x and y combination, is uncorrelated. This is, in finance, I will come back to this point, particular later on when we talk again about hedging, reducing risk. What we need to reduce risk, if we have more than one asset, is a negative correlation between x and y. Because then, if one is performing good, high returns, then the other has low returns, and you are compensating the risk. If one is losing, you can compensate the losses by the other which is doing good. So one precondition for reducing risk is negative correlation. And this was one fault, by the way, of all this design of CDOs during the financial or before the financial crisis of 2007 to 2009. You know, these CDOs, they packed together all these mortgages, subprime mortgages, and then they sliced it up and diced it and sold some part on the top, the good ones, because the repayments are first going to these tranches and then they trickle down, which are the more risky parts on the bottom. But this slicing and dicing and saying that these are good and on the bottom they are the bad only works if all these elements inside this box, these subprime mortgages, are negatively correlated. But it turned out that they were not negatively correlated, because if all they are going down, well, even then the good ones on the top have no value. And that is what was the case. German banks only holded the AAA tranches of these CDOs. But if they are all correlated and the market goes down, well, then even AAA is nothing more worse than the bottom. Yeah? And the fault was that they assumed by construction, well, they are negatively correlated, but in fact, they aren't.
Just one technical question. How can we differentiate this rho from P?
Well,
Because you said rho is like
P is P. And this is the Greek rho. Can you differentiate now rho and P?
yeah, just this.
Okay. So this is the Greek letter rho. You know, in my class, you even learn Greek. That's unbelievable. Okay. So just keep in mind, if we have more than one asset, we have also to think about the covariance, or if we standardize the covariance with the variance of the assets of x and y, we get the correlation coefficient that tells us about the correlation, the connection, the relationship between two assets. If we have three assets, we have a three-dimensional space, right? If we have four assets, we have a four-dimensional space. I cannot illustrate this graphically, but mathematically it's no problem. I do everything, even n, yeah, n dimensions.